delay. Key technologies we talk about here, NVLink. It is a proprietary NVIDIA protocol. Another one is ultra accelerator link, and lately scale-up Ethernet that came into this, like this protocol that these GPUs use for their communication. It is basically a version of the PCIe, Peripheral Connection Interface Express, kind of a technology. We are seeing also co-packaged optics being talked in this space, and we will talk about that later. So let's look into the details of this rack scale solution. This is a typical NVL or typical server rack based on the OpenOCP rack standard. There is a vertical power distribution port or distribution bar in the middle, and then we have here at the back, these are called the NVLink cartridges. These are the scale-up network cartridges. And inside these cartridges, we have basically, these are in this the NVIDIA version, there are 5,000 energy efficient. They mentioned coaxial, but I looked into it. It is basically a twin axial cable. There are two copper cores inside each cable, and each enables GPU to GPU communication. So it is not a twisted pair. It has to be a coaxial or the twin axial cable for this low-loss communication. And what happens is that these NV trays, they just slide into this one. They have blind mate connectivity. That means that you don't have to align it. As you slide these compute shelves and the switch shelves, they just dock into the place, and then they make this, all the GPU servers, they are connected to the switches, and then they are interconnected. Next generation scale-up solutions most probably will need, right now it is all copper and vertically integrated, but we expect this backbone to change in the future to optical fiber replacing copper when we want to go for multi-GPU, multi-rack systems. But right now, copper is doing the job that is needed for the single rack solutions. If we look into the AI server evolution, we started here. I remember when I started looking into this 2022, DGX H100, there was this data center graphic accelerated servers, or they was A100 and they released H100, 200. But these are basically 8 GPU compute platforms. That's how it started. And then NVIDIA released the NVL or Blackwell platform, which was the first kind of, it is a vertically integrated single compute platform with 72 GPUs. And this has been shipping this year, early this year, end of last year to this year. And this is becoming one of the workhorse force of the AI compute workloads, basically. Next year, NVIDIA is releasing a version they call NVL 144. What they do is that they are not increasing number of GPUs, but the GPU dice, they are increasing it. But as you see from these guys used to be 10 kilowatt each, 10 kilowatts. We were seeing a data center rack 40 kilowatts. NVL 72 requires 120 kilowatts. Vera Rubin, that's called 144, is going to require 132 kilowatt, a lot of power. And the next generation, which is 2027, they are talking about 600 kilowatts. So power is kind of going over the roof for these compute platforms. But what is also the scale out fiber connectivity is also increasing. 384 fiber to 1000 fiber, which we expect is the 2027 version will be over 5,000 fibers. And these currently they use the copper for the scale-up networks, but we are going to see how it's going to evolve in the future for the fiber. Are we going to see optical backbone for these racks or not? That is going to be up to time. So that is NVIDIA sides, but the industry is kind of catching up in the single cabinet solutions or vertically integrated solutions. If you look into the AMD world, we have seen this, the 2025, they released their Turin rack. It is a rack 120 GPUs, but it is not really a true rack scale solution. A rack scale solution means every GPU is connected through a backbone. So this one was a one rack solution, but each compute platform here, they are 8 GPU domains. So it is not acting as a single domain. Like it's not all 128 GPUs, they don't act as a single GPU, from my understanding. What they are planning is 2026, their Venice platform that is going to be the first vertically integrated. They call it the Helios rack. It is going to be the competitive product for NVIDIA's next year release product. And it is going to use a protocol called UA link, Ultra Accelerator Link over Ethernet. So this is the more industry standard protocol that the GPUs will use communicating among themselves. And they are going to also use a switch for scale-up network based on Broadcom's Ethernet Tomahawk 6 switch, basically for the scale-up network, which NVIDIA uses NVLink switch. And we see that their roadmap also shows more vertically integrated compute racks. And in 2027, AMD is also continuing this way of vertically integrated single GPU domain solutions. So, can we still, okay, we are talking about here 256 GPUs, but okay, what is the limit? So, using the standard spec connections, the Ultra Accelerator Link has a vision to connect 1024 GPUs in a single GPU domain. And if using an Ultra Ethernet, if you're connecting multiple racks, they are planning to reach up to 1 million GPUs. So that is kind of the vision in the industry. Okay, how can we build this AI workhorses to millions of GPUs? And the Ultra Accelerator Link and Ethernet, these are the more standard-based solutions that we are waiting to see the products in the industry yet. We expect to see them in 2026. While UAE Link has been trying to come up with solutions, they released this standard in 2024. Broadcom recently they released a switch called Tomahawk switch, and they also released their protocol scale out and scale up with Ethernet, more standard space protocols. So the objective of this Broadcom switch is the release was that it is their latest switch that has 64 ports of 1.6 terabits optical engines. These are 16 fiber. Uh, what is it? Ports. And if you think about this one, we are talking about 1024 fibers per switch. So objective is that the aim is to have a scale up switch in the middle of the rack, and then now you can use a scale up. But if you have multi-rack switches, you can use the Tomahawk switch, same switch ASICs across the network for both scale up and for scale out, and grow the network using common standards compliant components. How are they going to do this one? Let's look into this one. Broadcom switch is a 102.4 tera switch. This is the latest, greatest switch type, basically 64 times 1.6 teraport switch, and it is designed for high throughput, low latency, and from going from 72 GP per rack. If you think about this one, we want to go 72. In the version of the Broadcom, we are talking about 64 GPs per rack. So we have to have multiple racks in this design. So 8 racks in this design. This is a 512 GPU design. So you have to have 8 racks, and we have to have scale up switches in the middle of this row, basically. And one thing important is that all the GPUs here, or XPUs, they should have an optical attachment unit, direct optical connection. So which means that every GPU here is going to be connected to this middle of the row using optical fiber. A single copper or twinaxial copper is a good solution for a single vertically integrated solution, but copper has this limit of 1.5 meters, especially direct attached copper cables. And if you want to have these closely coupled large GPU domains, then we have to go for an optical solution. Some people might ask, okay, what about active electrical cables? That might be an option, but think about this one. An active electrical cable is 10 millimeter diameter, and then we have to bring in here, we are talking about here 49,152 fiber strands in this design. If you divide this one, we have to talk about 25,000 10 millimeter copper cables connecting in this entire network. It will be it is not going to be very effective and practical. And second problem with the active electrical cables is that here you see optics connected to the switch. There is no what is it? It's with the co-package optics. It is end-to-end integrated, so it is the lowest latency. With the active electrical cables, you have to use some sort of signal cleaning, and it adds the latency. So that is not going to provide the lowest latency that these AI clusters provide. So we expect that the future solutions, large GPU domains, they will need co-package optics, means optical transceivers embedded or connected closely meshed with the GPU on one side, and it will be connected to switch on the other end and provide the fully optical AI clusters. So let's have a recap of the key technologies in the scale-up networks. As I said, NVIDIA uses NVSwitch, which is a proprietary solution. It has been around since 2018. It's a proprietary solution, but it's a very mature solution, and it can support up to 576 GPUs now. So we are going to see how this ecosystem is going to evolve. Broadcom, which released their scale-up Ethernet solution this year around June 2025. It is the silicon is available, the chip is available, so it is up to the manufacturers to develop the scale-up switches, and it can support up to 1024 GPUs per cluster in one GPU domain. And it is a standard space Ethernet-based solution for the organizations who wants to build AI clusters using standard network gear. Ultra Accelerator Link is a protocol was developed basically by the Ultra Accelerator Link Consortium, member of AMD, Intel, Meta, Microsoft, and Hyper customers. It was integrated into Open Compute projects and early expected deployments in 2026. So this is another solution. And it is backed by the key powerhouse consortium members, and it's becomes to become a key player in the hyperscale area. So we are going to see how this ecosystem is going to evolve over the next years. That's about the scale-up network in the AI clusters. Let's jump into the scale-out network, what is happening in this world, because we want to go to million GPUs. That is the dream in the industry. And then let's see how to make that happen. So in a traditional sense, if you look at that, AI clusters, they first emerged a part of the traditional three-tier data center network. So they were in the traditional network, which was designed for north to south traffic, client server architecture. We used to have compute and storage, and we had this experimental AI ML machine learning clusters that were hooked into the leaf and spine architecture. And basically in this architecture, we generally have a top of the rack switch and a leaf switch and a spine switch, and then it's a three-tier architecture. And the new clusters, they are added to this by adding new leaf switches and that are connected to spine level. They were optimized for north to south traffic. But the AI networks, they need more like east to west traffic, and they need a different kind of network. And this top of rack switches, which is basically the standard practice in this traditional network, is redundant in this AI ML clusters. So what happened is that when the AI ML clusters started to form their own networking, the first thing that happened is we got rid of the top of rack layer. So basically the AI servers, they had their front-end connection. through the traditional network, leaf and spine architecture. And the backend network where the training happens, the servers, they were connected to the leaf network directly. So there is no top of rack top of rack server in this architecture. All servers, they are connected to the leaf network directly, and to have larger I would say the backend network architecture, we add a spine level to this backend network and then make it a two-tier network. And if you look at here, the speeds, the front end network doesn't need high speed basically. I think 10 gig, 25 gig, 100 gig, 50 gig to 100 gig is the main speeds. These days it's 100 gig basically. But the backend network, the speed last year was 400 gig. This year we are seeing 800 gig connectivity basically. And the key this kind of architecture is ideal for distributed systems and prioritizing the scalability. Like we can go up to 100,000 GPU clusters and they are fault tolerant. Key technologies that we see here is Ethernet, but the most known is InfiniBand based on this part, high performance computing area. We see a lot of InfiniBand, which is a proprietary NVIDIA technology, and RDMA, remote direct memory access, which is also an InfiniBand technology. A modified version of it is RDMA over Converged Ethernet, is also coming up as a more standardized solution. We also see here in this backend network shufflebox solutions and leaf and spine architecture with the elimination of the top of rack switch. So the key change in this network is we don't have any top of rack in the AI clusters. So we have seen, I think you might have heard a lot, the AI factories has arrived. And this is basically a very modular design that NVIDIA had been, I would say, evangelizing or promoting to a repeatable pattern, like a pod design, a compute, there is a row of compute racks that are connected to end of the row or sometimes middle of the row of networking gear, and then it is a closed like a unit which is called a scalable unit. And in a, for example, a scalable unit, there are 16 racks, 8 on this side, 8 on the other side, and 1152 GPU acting as a single GPU. And this can go up to, let's say, we can call about 18,000 GPUs, basically. This become one of the blueprint for the industry, and then the customers, they started to create their own versions of networking architecture. So there is one caveat with the spine and leaf architecture. So that is basically the key. I would say the spine and leaf served the industry quite well for over the last couple of years. But the main issue or the way we build is that every time you build either for front end or back end, we have to put the spine level at first on day one, and then we add the leaves to the spine on day two. This is like grow as we grow the network as we need it. So that means that let's say if we put in today a 400 gig spine, let's say if you put in, and then in 3 years time we have 800 gig leaf networks, how are we going to integrate it? So that is the biggest issue with the spine and leaf. Day one, the entire spine has to be put in place, but it is very costly to remove the spine or refurbish the spine to upgrade to the higher speeds. So what can we do about this one? Before that one, I think I will come back to this one. There is one thing in the industry. I think Google thought about this one a lot. They said, okay, we do spine and leaf. We install it day one, but it is really difficult and costly to upgrade. So how can I do this one? Some of you might have heard a direct connect architecture for scale-out network with optical circuit switches. So what if I put optical circuit switches at the spine of my network, instead of the traditional switch. These are passive switches. And then I built my aggregation network. Like today, I have a 100 gig backbone for this network. I have 400 gig. Tomorrow, I might have 800 gig. And then I connect these clusters using a passive optical circuit switch. So the way it works is that an optical circuit switch is a passive device basically. What it does is that an incoming beam of light is redirected that enters in through fiber through optical mirrors to the outgoing fibers. So basically, whatever comes here as a light goes to the is directed to another output port using these optical mirrors, MEMS, mechanical micro electromechanical mirrors, basically. And what you do is that as we build new aggregation blocks with new speeds that support higher speeds, like 400 gig today, or we had 100 gig aggregation blocks in the past, we can connect them optically, like physically, and then we don't have to change our backbone or the spine of our network. This gives quite advantage to have this multi-generational optics in one network. And but there's always a but. We have to know. This is the one they use in a bi-directional transceivers are used in this kind of a network architecture, and they use some sort of circulator. So these are like single fiber systems, and then transmit and receive their multiplex onto a single fiber, and then that's how it is used. I think there are also different versions of it, the duplex systems as well. We see them available in the market. But the most, if you want to cut your fiber density by half, these are basically WDM based and simplex systems, like bi-directional systems. Supplier base for these ones will be a bit limited compared to the typical transceiver, so it might cause a couple of other supply chain challenges. But overall, optical circuit switching is a circuit switching. It doesn't know the data package going on it, so basically it is fiber to fiber connection, but automated patching, we can think about it. It supports spinal leaf and mesh topologies, and it's a dynamic topology. It allows dynamic topology design. Basically, you can grow 100 gig today, 400 gig, and then 800 gig tomorrow in your aggregation blocks, and then you can kind of don't have to change your backbone at all, basically. Multi-generational optics will be used in the same fabric, but you have to know how to orchestrate the live traffic, live fabric. I think this is the part which requires a little bit specialized know-how. How do we make sure that the data package switches here, active switches working on this, the aggregation level, will be able to talk to the optical circuit switches. And it is not wire speed. This technology is not wire speed. So there is the latency is higher. So it is not conscious of the package. So it needs a bit more, I would say, engineering and design. So if you want to get more information about this technology, you can always go to Google Jupyter Evolving. I think they have detailed white papers on this architecture. So before we go further, I want to go back, take one step. I changed the order of the slides for some reason. Let's compare Ethernet versus InfiniBand for scale-out networks. Because as a customer, we have to make two choices. An InfiniBand solution is basically it's a really low latency, high performance computing solution developed by NVIDIA before it was Mellanox. It is its best solution for tightly coupled GPU clusters, supports 800 gig per second. It's a lossless technology and congestion managed. I mean, the key advantage here is that I look deeper into this one. The InfiniBand protocol, basically, they don't transfer any packet until they get it's a policy-based switching, basically. If they don't know the receiver is ready to receive a package, they don't release the package. So it's a very lossless protocol. which is critical in this the GPU clusters. It supports tens of thousands per nodes, and it is very low latency, like 0.5 to 1 microseconds. And it is basically Quantum X is the switch family. If you see in the collateral, this is basically the switch in this space. Ethernet, on the other hand, is widely adapted and it is playing a bit of a catch up in this field with the RDMA over converged Ethernets. And then we started to see that NVIDIA also started to support Ethernet with their Spectrum X family. And it is also highly scalable. There is industry-wide know-how. And basically, cost is lower since there are more vendors in the ecosystem. It is not proprietary. And most switch and ASICs manufacturers, they support this technology. So that is about InfiniBand and Ethernet. Let's move forwards. Previously, I talked about millions of GPUs. On the right hand side, I did a little bit of a copilot search. Okay, give me the number of the largest known GPU installations 24, 25. You can see here OpenAI, Stargate, they are talking about 100,000 GPUs. Microsoft Azure, they call 120,000. Oracle MGX, like 500,000 GPUs. So we see that this number of GPU clusters is growing. So how can you build this kind of stuff? So that is called scale out sites. I think we can't really build these large clusters in one data center. So we have to build multiple data centers in a campus. Plus, we also have to build in a region, basically. This is, let's say, roughly 100-kilometer radius radius area is kind of a sweet spot that's kind of the most people are trying to put their clusters and to build these large GPU clusters. This is one thing is one area is not enough because power is not available there. So can I get enough power within this range? And then how can I build these large clusters? So this power availability is one thing, and the second thing is space availability. But it comes with its own requirements. We have, if it's a campus installation like this, we have to build high fiber connectivity between the buildings. That requires high fiber count trunk connectivity. If it is a metro area, then we need to use this long haul high performance fibers like the TXF high bandwidth fibers. And how is Corning preparing us for these large clusters or AI scale cabling? Let's look into that one closely and we will wrap it up for our session. We have solutions for the pod level or the indoor solutions. Basically, we have these indoor solution sets. The key thing about the AI clusters is that they want to connect the server to the leaf switches with the point-to-point connection without any patch panel. And for these purposes, we have these backend network connections we call core trunks. These are up to 144. One side is connected to the server, the other side is connected to the leaf switch. I mean, you can do this one using point-to-point jumpers, but using a bundled approach like this, you pull once and then plug the connectors. In this case, you still have to bundle it and then plug them. It takes a lot of time. For the leaf to spine, we have these patch panels, our standard Edge 8 solutions. Today, we see most of these 400 gig and 800 gig solutions. They are 8 fiber based systems, basically. So Edge 8 works pretty nice here. For the scale out parts from leaf to spine, sometimes we use CWDM based connectivity. So Edge 8 provides that MTP-to-LC breakout as well. And basically, this is within the data center. But if you want to go large and really large clusters, we have ultra high density solutions using MMC connector. So this is a new connector. It's called mini empty connector or like tiny empty connector. So it is one connector is the size of three of these one is kind of the size of a one MTP footprint. So in a 2U rack like this, we can terminate 2,304 fibers. And coupling them with or matching them, connect them with the high fiber count trunks with MMC connectors, we can terminate up to 40,000 fibers in these racks. So we also provide these racks. We provide them with pre-configured with the racks and the patch panels. They come on these racks. You only have to pull in the trunks and then connect them. There is also shuffle box solutions, which is port breakout solution basically. In the edge footprint or a completely integrated solution set, and also special breakout harnesses if needed for these AI clusters. We released a cabling guide that is released last year called AEN 185, and it is basically so 30-50 pages document. It details out the entire products, part numbers, and polarity schemes as well. I think it's a good guide to read it. And our team is working on some new cabling guide for the NVL72 racks. That is either ready or almost ready. I think we can ask Cindy. That will be coming soon. That is also going to detail out the entire architecture and the required cabling components for this NVL72 type cabling in the AI clusters. I think that is the end of my slides. We reached the end. I hope if you survive with me till the end, and we can have your questions if you have something for me. Let me stop this part. Yes, Cindy. You are on mute, I think.
In theory, I should. Can you hear me?
Yes, I can hear you.
Okay, perfect. It was just probably stopping the recording. Thank you so much for a lot of very detailed insights. We do have few questions today, but maybe let me take your comment on the NVL72 cabling guide. It's just kind of in its very last minutes before we publish this, so this will come out very soon, and we will share this via our website. So if there's interest, we can certainly share this also via email to our customers. And then while there are still some questions coming in, maybe I start with the first one. It's product related. Do you see in the future any change in kind of the hardware or housing design based on the technology that you talked about and the impact and scale of AI networks? You talked about very small form connectivity and some of the other products. Yeah.
I mean, we are already seeing that, Cindy, because MTP was the dominant connector last 10 years. But the density requirement, like we are talking about 40,000 per rack. In a server rack, if you need to bring 1,000 fibers, it is not very feasible using with the MTP base. So we see more and more MMC type of hardware and connectivity, and that is going to be more common. And we released already products, and we will have more standardized solutions next year. So yes, the density requirement, fiber count explosion is requiring new hardware, and MMC is becoming the connector choice for this new hardware.
Yeah. Okay. Well, I think we start seeing this already popping up, and as you said, it's going to be more of this in the future.
Yes.
You've touched on Ethernet and InfiniBand standards as well. Will they keep coexisting, or do you see one of them, becoming the prominent standard in terms of AI factories?
Yeah. I mean, InfiniBand has inherent advantages, I think, for certain high performance computing. As a protocol, it is a very efficient protocol. So special applications, I expect that the InfiniBand is going to stay. And NVIDIA roadmap supports both. So they have a roadmap for Ethernet and they have a roadmap for InfiniBand. But they are more focusing on Ethernet because the industry is kind of going for Ethernet, and then they are just here listening to their customers and releasing more. Spectrum-X is the one which you can see in their roadmap is Soviet GTC. They released more high-end Spectrum-X switches. So I think latest last year when XAI they released their data center, they used Ethernet. So we see more and more Ethernet, but the InfiniBand is going to be maybe specialized high performance computing clusters solution.
Okay, thank you. And then there's another one that is related to sort of existing data center starting to deploy cabling solutions for AI. I know in many cases, if it's a dedicated network, there are going to be like new builds.
Mhm.
Do you have any comments on this one, existing versus new?
The existing one, the key challenge in the existing networks is the power densities. I mean, the rack dense power for rack density, it is difficult to bring it. Like previously, the racks they were designed 15 kilowatts. So we are talking about 120 kilowatts per AI rack. So customers they will have to distribute those racks. Okay, they will have to, if they want to use the existing footprint, so they can put one or two racks per row. So they will have to use this fiber connectivity. So it won't be really very efficient. And will they have the liquid cooling? Because all these racks they come with the direct liquid cooling. So or if they use the air-cooled solutions, AI servers, they will still have to spread them across the brownfield installations. That will need fiber connectivity. That is, I think, since they are not that dense, they can still do with the MTP-based solution. But if they are building a new solution, a greenfield, then they will have to definitely consider the density, power requirement, and cooling requirement.
And wait, not to forget if you add
Oh,
all these
yes.
elements to it, because
Yes.
you have to think about kind of the structural building of the data center if you
Yes.
want to start utilizing this as well,
Yes.
right?
Yes, exactly.
Yeah,
But
okay. So then there's another question with respect to link loss budget. Do you see any particular challenges upcoming when we talk about AI deployments and AI scale outs and scale ups?
the key thing on yeah, that's a really good question. The optical budget is very sensitive in these AI protocols. They are very sensitive to packet loss. If you have heard anything about port flapping, like an optical port going up and down, so it is one of the main concerns. So you don't want that thing to happen in the middle of a training session because it slows down. So the application best practice customers they use is this direct connection, especially at the server to do leaf switch. So that's why we have this core trunks. Like these are like meant direct connection. You don't have any patch panel in between to minimize any, let's say, port flapping happens due to possible reasons. There are transits, the laser might not be strong, the receiver might not be strong enough, or the optical link might be a bit of a weak. So the best way to at least using direct connection with the optical trunks or patch cables, you at least minimize the physical infrastructure risk, and then that is one practice we see a lot from our customers. And in certain cases, they try to minimize the number of patch panels. So, can I have one patch panel connector pair between my leaf and spine? In those cases, we see some customers might be using splicing with preterm solutions. So, that is a combination of preterm plus pigtail spliced to the high fiber count cables. So, yes, optical budget is these workloads are very sensitive to these port flapping. That's why the customer's best practice they want to minimize the number of patch panels between these systems.
Yeah, okay. Um, we do have another one, which is probably a bit tricky to respond to. You talked about very small form factor MMC connector and products, and the question is like whether those would currently be sold to all customers. Now we know that the really big customers, the really big deployments out there will require a lot of that connectivity.
Mhm.
And there's only so much capacity in the markets. So that's probably something to keep in mind. Your take on this question?
Yes, MMC is becoming. I think we have seen last year at Eco couple of vendors they were using on the transceiver side, so it is getting into the transceiver side, and the industry is also adding capacity to increase the increase the output of this MMC connector. Next year onwards, I think we will be in good supply of the connector. And as Corinng, we are also releasing our MMC-based solutions as well to our customer base. Basically, that's our plan to release those solutions. So yes, I think it will be our next generation solution.
Okay.
Okay.
I think that's all the questions I can see in the chat. We still have a couple more minutes. If there are any additional questions that you want to raise, then please just type them up and we're happy to moderate them. And of course, you always have your very skilled Corinng team at your hands, so you can always drop us an email. You can speak to your local Corinng salesperson for more details, and they can refer any questions back to us if need be, or respond. So whichever feels most comfortable, we're here to respond to any additional questions if you have. And if I don't see anything else incoming, then we can basically wrap this up. Thank you so much for participating. Thanks, Mustafa, for giving us insights on the second topic for AI. There will be one more session in November, so stay tuned for another invite on the third part of the series. And we hope to see everyone who dialed in today back in November. Thank you so much.
Have a nice day.
Have a nice day.